Part A asks to find the probability that exactly 8 students are left-handed out of this class of 15. So we're told that in this particular high school in Victoria, Australia, the probability of a student being left-handed is 0.475. That seems high. 47.5% of students are left-handed in this school. And we need to determine that out of a particular class of 15, the probability that exactly 8 students are left-handed. Okay, I can see here that this is a binomial distribution question, and the reason that I can see that is that it has a couple of important characteristics. The first is that we only have 2 outcomes, either left-handed or right-handed. And in a binomial distribution question, we either have the probability of success, which we call P, and the probability of failure that we call Q. So our probability of success will be left-handed, so that'll be 0.475. And our probability of failure will be 1 subtract 0.475. So that's the first sort of characteristic of a binomial distribution that I can tell here in this question. The other characteristic is that we have a number of trials. In our case here, we have 15 students. So we have, it's like if you were flipping a coin, say 50 times, and then we have 2 outcomes, heads or tails. That's a sort of a good sign that it's a binomial distribution question. And likewise here, we have 15 students. So our number of trials, n, is going to equal 15. Okay, so looking at the solution here, let L be the number of left-handed students in this class of 15. So we have, and this is the notation that reads, the number of left-handed students is distributed as a binomial distribution with 15 trials with a probability of success of 0.475. So that's all that this means here. That looks a little bit intimidating, but if you just read it out, that's essentially what that means there. Now, to find the probability, we want to find, so the probability of L, the number of left-handed students equaling 8 exactly, it's going to be equal to, now we're going to use the binomial PDF command on our calculator to solve this. So we use binomial PDF when we're looking for an exact number of successful outcomes rather than a range, which then we use binomial CDF, which we use in part C. So the number of trials is 15, the probability of success is 0.475, and the number of successful outcomes is exactly 8. So let's go ahead and enter this into our calculator. Okay, we go menu, number 5, probability, number 5, distributions, and we go down and we choose binomial PDF. Number of trials, 15, probability of success, 0.475, and the number of successful trials is 8. Hit OK, and we get an answer of 0.183, and that's that answer there. So 18.3%. Okay, that is the answer to part A. Part B, similar to Part A, this question, it asks to find the probability that out of a class of 15 students, there are no left-handed students this time. Okay, so I won't go through all the detail that we talked about in Part A. So if you're not sure how I got these values here, I recommend going back and watching Part A. But just in a very quick summary, we know that this is a binomial distribution. We have a probability of success, which represents the left-handed students being 0.475, and the number of trials, n, being 15, that represents the 15 students in the room. So we want to find the probability that there are no left-handed students, so L, which we defined as the number of left-handed students in the class back in Part A, to be equal to 0. And similar to Part A, we can find this using a binomial PDF command because we're looking for an exact number of successful trials, being the exact number being 0. So it's actually very, very similar to Part A. Number of trials, 15. Probability of success, 0.475. But this time, the number of successful trials being 0. So let's go ahead and enter this into our calculator. We have menu, number 5, probability, number 5, distributions, and we choose binomial PDF. Number of trials, 15. The probability of success is 0.475. And the number of successful trials we're looking for is 0 left-handed students. Hit OK, and we get this number here. Okay, so this is quite a small number. This is 6.34. I'm going to round it to 3 significant figures. 6.34 times 10 to the power of negative 5. Let's just write this out. So 6.34 multiplied by 10 to the power of negative 5. So this number was so small that with my current calculator settings, it actually gave me the answer in scientific notation. Now, if you left your answer like this, that would actually be fine. That you would get full marks for that. The question doesn't specify that you should leave your answer in a particular form. I have decided to leave my answer in decimal form, but if you decided to leave it like this, that would be okay. I'll just show you how to convert this back to decimal form. This number here is quite a small number because we have a power of negative 5. If it was just to the power of positive 5, it would be a very large number, something like 634,000, or maybe it's 6,340,000. It's one of those two. But this one is a very small number. So it's going to be 0.0000, a certain number of 0634. So in front of this 6, I like to write some zeros here. I'm not sure how many yet. Let's just write some out. And the number of times I move the decimal point to make this number smaller, or move the decimal point to the left, is the power that we have. So 5 times. So it's going to be 1, 2, 3, 4, 5. So the decimal point is going to be there. So it's going to be 4 zeros. So 0.1234634. And that is how I got this answer there. Okay, that is the answer to part B. Part C. Find the probability that there are more right-handed students than left-handed students in this class of 15. Okay, so looking at the solution here, I've said that since L, back from part A, represents the number of left-handed students out of a class of 15 students, the number of right-handed students can be expressed as 15 subtract L. So for example, if L was 0, no left-handed students, then the number of right-handed students would of course be 15 because all the students are right-handed, so 15 subtract L. On the other extreme, if there were 15 left-handed students, the number of right-handed students would of course be 0 because no students are right-handed students, and therefore it would be 15 subtract 15, which is 0. Or let's pick a sort of middle ground number. If L, the number of left-handed students, was say 5, the number of right-handed students would be the remaining 10 students, which we could define as 15 subtract 5 is equal to 10. So I've just sort of said here that the number of right-handed students, instead of introducing a new letter, a new variable like R, we can actually keep it as one variable and express the number of right-handed students as 15 subtract L. So in order for there to be more right-handed students than left-handed students, this expression here needs to hold. So the number of right-handed students, 15 subtract L, needs to be greater than the number of left-handed students. Now, if I do some algebra here and rearrange, I won't go through all these steps here. It's actually pretty intuitive. The number of left-handed students needs to be less than 7.5. Now, since you can't have half a student, the number of left-handed students needs to be 7 or less. You may be thinking, well, I kind of knew that intuitively. I don't really need to go through all this working, and that would be fine. If you just, at the start of your question, said, well, in order for the number of right-handed students to be more than left-handed, there can't be more than 7 left-handed, because as soon as you go more than 7, now you have 8 left-handed, which only leaves 7 right-handed. So the number here, the maximum number of left-handed students is 7. So we now need to find the probability that there are no more than 7 left-handed students. And now we're talking about a range of students. Unlike parts B and A that had a specific number of successful trials, we're now looking for a range of successful trials because the number of left-handed students could be 0, it could be 1, it could be 4, it could be 6, it could be 7, but can't be 8. So it's actually between 0, that's our lower bound, and 7, which is our upper bound. And when we're trying to find a probability of a range of outcomes of a binomial distribution, we use the binomial CDF command. C stands for cumulative. Okay, let's go ahead and enter this in our calculator. So we have menu, probability, distributions, and this time we're choosing binomial CDF. Number of trials, again, is 15 students. The probability of success is still 0.475. That's the probability of a left-handed student. Now, our lower bound is 0 and our upper bound is 7. We hit OK and we get this answer here, so 0.578. And that is the answer to part C.